Modern polymers are an essential component in sports and activewear across the world, and it is these that gives sportswear the desired characteristics that are necessary when involved in intense exercise. When you imagine sportswear, you would often expect a certain level of comfort and adaptability from the garment, a trait that you would be sure to find in many top brand labels such as Gymshark and Gym King apparel. So when we talk about polymers, what are we referring to? By definition, a polymer is a large molecule made by linking together repeating units of small units called monomers. Poly means many and mer means small unit. The process of linking together monomers is referred to as polymerization. Here, this is represented by the red lines, which represent chemical bonds, and the green circles represent monomers. So how do we classify polymers? Well, polymers can be divided into natural and synthetic polymers. I'll be primarily focusing on synthetic polymers, as a lot of the polymers in gym wear and sportswear, clothing and stuff like that is predominantly synthetic polymers, in particular step growth and chain growth polymers. But as you can see here, natural can be divided into DNA, protein and polysaccharides, and synthetic can be divided into step growth, chain growth or other. So what main characteristics do we look for when we consider gym clothing? Well, it has to be lightweight. It has to be waterproof, it has to be breathable, it has to be comfortable, durable, it has to be absorbent, and it has to move with you, so it has to be stretchy. So which polymers allow us to attain these characteristics? Well, the most common polymer type found in sportswear are polyesters, and this is due to their many beneficial characteristics, such as moisture management, their softness, their ability to insulate, their ability to dry fast, and how lightweight they are. Step growth polymers are also found in activewear when we consider breathable fabrics. Whilst we're on the topic of breathable fabrics, let's have a look at how polymers allow a fabric to be both breathable and water resistant. Breathable fabrics are important in activewear as they are designed to resist water penetration but allow the passing through of water vapour from evaporating sweat, as well as air to assist in keeping the wearer cool during exercise. This is achieved through fabric polymer membranes such as microporous membranes and hydrophilic membranes. I'll first talk about microporous membranes. Microporous membranes have tiny holes in their surface that are smaller than a water droplet but larger than a gaseous water vapour molecule. Common microporous membranes are synthesized from polytetrafluoroethene, or PTFE, and polyvinylidene fluoride, or PVDF. These are both examples of chain growth polymers. So how do we synthesize step growth polymers such as PTFE? Well, for that there are multiple methods, however I'll be focusing primarily on radical polymerization. In this, a reactive radical species is formed from the homolytic bond fission of a peroxide such as benzyl peroxide. Next, a radical species reacts with the electron-rich double bond of the tetrafluoroethene molecule to produce another reactive radical intermediate. In each propagation step of the synthesis of PTFE, the initiated radical adds to another molecule of polytetrafluoroethene, and this generates another terminal radical which can then propagate further. In the termination step of radical polymerization, polymer growth termination can occur in two different ways. The easiest of these is chain combination, in which two reactive radicals on different growing chains react together to form one single long chain. The other method is disproportionation, where a reactive radical on a growing chain abstracts a fluorine off of another growing chain. This results in one chain being oxidized and the other being reduced, hence disproportionation. Next, we're going to talk about hydrophilic membranes and how they affect the breathability of a fibre. Hydrophilic membranes are thin films of chemically modified step growth polymer such as polyester or polyurethane. An example of a step growth polymer that is incorporated into a hydrophilic membrane is polyethylene oxide, which constitutes the membrane by forming an amorphous region or a region of undefined shape. This region forms intermolecular pores to allow passage of water vapour but not liquid water. If we look at the synthesis of polyethylene oxide, we can see it as a simple self-condensation reaction in which multiple molecules of the monomer polymerize upon the elimination of water. Next, we're going to look at the polymers that make sportswear stretch, the most obvious of these being elastane, spandex, lycra, or whatever you happen to call it. These all refer to the same polymer in this case. Spandex, an anagram of the word expands, provides an extraordinary elasticity in activewear to reduce restriction of the wearer's movement. Invented in 1958, it has an extension at break value of greater than 200%, so in scientific terms, it's quite stretchy. Chemically though, it is a very interesting polymer. It is a synthetic linear molecule that consists of a chain containing at least 85% segmented polyurethane. It has alternating hard and soft regions linked by urethane bonds. The hard regions provide fibre strength and long-term durability, and the soft regions give the iconic elasticity to the fibre. Most garments, including swimwear, gym wear and scuba suits, contain approximately 5 to 7% elastane. So what about fast-drying polymers? Well, an example of a polymer that provides both comfort as well as fast absorbance to the fibre is viscose. Viscose or rayon is a lightweight, semi-synthetic polymer that aids with fabric breathability, absorbency and comfortability. It is the perfect material to incorporate into gym wear fabrics as it is soft and comfortable due to it being derived from cellulose or cotton. So looking at the synthesis of viscose, we can see how cellulose is chemically modified to make viscose. It is a relatively simple reaction in which cellulose is reacted with 6 equivalents of carbon disulfide and sodium hydroxide respectively. This process eliminates 6 equivalents of water, making viscose a form of step growth polymer. This is a potential reaction mechanism, as I'm not 100% certain it's correct, however it was what I was originally considering. In this mechanism, the lone pair of electrons on the cellulose hydroxyl group is pushed onto the delta positive carbon atom in carbon disulfide. This in turn pushes the electrons onto the delta negative sulfur atom in carbon disulfide, which gives us the negative charge that we see in viscose. The hydrogen atom in the OH group then splits off, giving its electron density back to the positive charge on the oxygen. So how does viscose absorb water then? Well, it turns out viscose is 60 to 70% amorphous, due to it having a very similar structure to cellulose. This means there are a larger number of micropores produced in the fibre, and therefore a higher probability of these pores to be larger than a water droplet. This ultimately results in greater water absorption. Thank you everybody for watching. This marks the end of the video. I hope you learned something today. Cheers.